So as I mentioned the other day, multiple regression is by far um, it's much more common than is just the bivariate case that we looked at last week. And I don't know, I can't think of an article that I ever worked on, or a manuscript that I ever worked on, or in fact a manuscript that I ever read, where the researchers just reported a bivariate regression. It would almost be, it almost make more sense just to do a correlation, and unless there was, you essentially get the same information. If the information that you want to get, which in most cases is probably what is of interest, is is the relationship between the two variables meaningful or not? Is it greater than we expect to get by chance? And if you wanted to do a null hypothesis test, you could just do that pretty easily with um, with a correlation. So my sense is that's probably what happens more often. So this is by far the more frequent um, case. And in the case of multiple regression, we're able to examine the effects of one independent variable on the dependent variable while controlling for the impact or the effects of several other independent variables. And so it's a handy little thing to have when you're assessing the impact of one independent variable on the dependent variable, is to be able to say it's the impact of that independent variable on that dependent variable while controlling for or while holding constant the other variables that are in the analysis. And so we'll talk a little bit more about that as we move forward, but it's a it can make for a very powerful analysis, because somebody could say that, maybe the reason why your independent variable is related to your dependent variable is because of, I don't know, level of education. And if you have level of education in your analysis as another independent variable, you could say, no, it's not, because I'm controlling for that. And try again. And so it does allow for a more I think persuasive argument regarding the relationships between independent and dependent variable. Um, but it really doesn't get us, and we'll talk about this when we talk about ANOVA as well, and we talk about analysis of covariance as well. It doesn't get us any closer to the causal connection, right? It doesn't. Anybody remember the three criteria for causality? We need to first do what?
The one precedes the other.
So time order, the and so the dependent variable has to happen in time right after the independent variable.
Then I need to exclude all the other potential causes.
Yeah, so we call that spuriousness. We need to eliminate all spurious, and that's impossible to do, right?
Right.
All, right? We're not just saying three, we're saying all, and we don't even know what they all are. So that's why making causal, for one, don't ever say, and correct people when they do say this, and I would correct you. If you say my manuscript proves, prove is too strong of a word always, I think, and for the kind of work that we do. Maybe if you work in engineering and you're doing things with computers, and you're able to, or earth and energy, and you're doing things with rocks, maybe there's some proof that you can do there. But with humans, the word proof is, or prove is probably too strong of a term to use. But for sure, to say that I have proof that X caused Y is always going to cause you more problems than it helps, because you don't have proof. You might have you might even have done a really good experiment, but there's still, that still falls short of proof, for one reason, because you haven't controlled for all, or there might be spurious relationships that we're unable, that we just don't know about, that you can't tell me that you've been able to understand and control for all of those. It's just not a possibility. And so getting back to multiple regression, what's the third one, by the way? The correlation, what?
Randomization.
No.
No, that's for an experiment. Sorry.
Covariation.
More specifically?
X should cause Y.
No, that where we want to argue that X causes Y, we have to show three things,
As
right?
one increases, the other increases, or vice
Yeah, what do we
versa.
call that? What do we call that? Correlation, yeah. So we have to show that X and Y are correlated. We have to show that the X happens before Y, or the independent variable happens before the dependent variable, time order. And then we have to rule out spurious correlations. And so all we would get, even with a multiple regression where we included a bazillion other independent variables, we would still be sort of left with we have correlational data, right? Assuming that this isn't an experimental data, we're working with correlational data that's not from an experimental study. It's gathered using probably survey methodology as opposed to experimental methodology. We would only be able to say that our analysis shows that the independent and the dependent variable are correlated, and correlated even after we control for these host of other factors, which doesn't get us very far along in terms of the time order argument. It doesn't help there at all. It might help some with the spuriousness, but certainly you didn't control for all potential spurious causes. So a word of advice or a reminder probably for most of you, making the C argument or the causal argument is just probably, it's always I wouldn't even use the word in the paper that I was writing. I might say, I wouldn't use the word causal. I might say strong evidence for, that word causal would just ruffle too many people's feathers, really unnecessarily so. And then you could go down a rabbit hole in terms of, I mean, there's been books written on causality that would bore us all to tears, and we probably would only be able, written by philosophers mostly, and we'd probably only be able to understand, if we got through the first chapter and we understood half of what they said, we probably, even though we all think we're smart, we probably would feel, I actually have a book, and it's just called Causality. And how difficult could that be? It's just not my cup of tea for sure. After you get past, well, maybe I made it past the first couple of pages, but not much. Well, maybe a little bit better than that. But so just the point is this doesn't allow us to make the causal argument with certainty, even though we're controlling for these other things, and I think some people get confused on that front. So the dependent variable has to be metric, or as we talked about, it's got to be interval or ratio, right? Or at least you're willing to call it interval or ratio data, right? So it's the Likert scale that some might quibble with not being interval. You have to be willing to accept it as being interval level data. So the dependent variable is interval or ratio. The independent variables can be that interval or ratio, same level of measurement, or dichotomized, just like we talked about with bivariate regression. So just make a big note to yourself, circle it, underline it, star it, do whatever you need to do to make sure that you don't violate this on the homework number 2, because if you give me a nominal variable that's not been dummy coded as an independent variable, it's fatally flawed, the analysis is. If you give me a nominal variable, and SPSS doesn't know enough to tell you that don't do that. if you do a nominal variable or a dichotomy as the dependent variable, again, the analysis is fatally flawed. And so just make sure if you have questions, and maybe we'll take a minute on one of our breaks, we might take a minute and talk through a few of the analyses that you guys are going to do as we get a little bit further on. We'll talk through some of the analyses that you guys are going to do, and we will just make sure that everybody has a good understanding of that, because it really is it's critical. So we saw what the equation looked like that we use for the bivariate case, where we have predicted y is equal to some intercept plus some slope times some value. In this case, we have the same single intercept, a, so our predicted y is going to be equal to some intercept or constant, is the way it's recorded in SPSS, plus some b, or some weight, that's associated with some variable called x1, some independent variable called x1, plus some weight for b2 that's associated with some value for x2 or independent variable 2. And that could go out to k potential independent variables, and k could be quite large in some cases, but in most of the cases, in the social sciences for sure, I mean, I don't know, if I see 15, it seems like a lot. 5 or 6 or 7 is probably reasonable. I don't think we have theory that sort of goes beyond that in a meaningful way. Maybe there is that I've not been exposed to, but my sense is once we get beyond a pretty small group of variables, it ends up being more data exploration than hypothesis testing. So we will refer back to this when we actually have to calculate a predicted y, because SPSS is going to give us the intercept, and it's going to give us all of the b's, right? Just like we got one b when we did bivariate regression. In this case, we're going to get b's equal to the number of independent variables that you're working with. And so SPSS is going to give us the intercept and the b's. And then what you would do to calculate the predicted y, and again, we'll work some examples here shortly, is you would just plug in x1, x2, x3 up to xk, the values. And so let's say that variable x1 is education. You would plug, and we're working with case number 1 in our data set. We would say, what's case number 1's level of education? And we'd plug that in. And then let's say x2 is income. And we'd say, what is case number 1? What is that person's income level? And we'd plug that in here. And then we'd do the same thing all the way out to k independent variables. And then we would just do the math, and that would be our predicted y value. When we're doing research, we're usually not interested in calculating predicted y. We're usually interested in interpreting the b's, and you'll see that. I think it's you'll see why here as we work through some of this material. But we're calculating predicted y's because it helps us, I think, get that 40,000 foot view of what it is that ordinary least squared regression is doing. It's getting us the absolute, across all of our data, the best, the closest predicted values that we can possibly get. And so it determines this set of b's based on minimizing the residual. That is the difference between actual scores and predicted scores. So again, we're going to get back to that. If it's a little bit fuzzy, that's perfectly fine, and hopefully that won't be the case after we look at some real examples. And so in standard multiple regression, we just enter all of the independent variables into the regression equation at the same time. And so they're all entered in at the same time, and they as opposed to, and we'll talk about this at the end of some of the material we have for next week, there's some other forms of multiple regression where we might enter independent variables in blocks, and there's might be some theoretical reasons for doing that, and but that's sort of a hybrid approach. Use some. From my perspective, there's not a lot of advantages there unless there's strong theory that sort of drives that. And if that's the case, then it would make sense to do that. And the expectation is for the multiple regression, our expectation is that there'll be a statistical significant relationship between the set of independent variables and the dependent variables. The hope would be that the independent variables that were included in the analysis would, as a set, would relate to or help us understand the dependent variable in a meaningful way. And so we test that with an F-test, just like we did with bivariate regression. And the F-test is the test for, really is the amount of covariance, or R squared, between the set of independent variables and the dependent variable, significantly greater than 0. Significantly greater than we expect to get by chance. And we're almost always interested in having this be 0. There are ways to test if it's greater than some value other than 0, but it's almost always just going to be, is the R square greater than we'd expect to get by chance? And one way to sort of think about that, before we move on, one way to think about that is, and it would be pretty easy to do, we could take some dependent variable, and it wouldn't matter what it is, but some dependent variable from our data. And then we could take you could use the random number generator in SPSS and generate just a bunch of noise data, or just using the random number generator, right? So there's no signal there, it's just white noise, and we could plug those in as variables into an analysis. And would we expect there to be a relationship between that set of randomly generated variables and our dependent variable? Would we expect there to be a meaningful relationship? No, right? Because it's a set of we just use a random number generator and we generate random data, and then we use it as our independent variables. We wouldn't expect that relationship to be meaningful. That is, the relationship between the entire set of independent variables that we created and our dependent variable. We wouldn't expect that to be meaningful. But it's also not going to be exactly 0, right? Because the way that the regression analysis works is that each variable will reduce the sums of squares residual. It can only go in that direction. It can't make it worse. And so what we really want to know, and that's what the F-test is doing for us, is the relationship between the set of variables that I'm analyzing and my dependent variable, is that greater than we would get by chance? And by chance, it's just randomly generated data would be another way to think about chance. And so it's the first step that we will have to. It's the first step that we have to go through. We do our analysis and we look at the f-test. If the f-test is not significant, meaning the r squared doesn't vary significantly from 0, stop, you're all done. That's all the analysis you need to do. You didn't explain any variance with your set of independent variables. And so it makes 0 sense to continue to interpret those results because you didn't explain any more variability than a set of randomly generated data would or would not be able to explain. So that's sort of the first. We have to sort of we have to cross that threshold, and then we can go on to interpret the regression analysis. And so that's what I'm saying here. If the R square is significant, that is that f-test. If it's significant, we interpret the individual relationships of the independent variables with the dependent variables. And we do the same thing. We do a t-test to test whether the individual relationships between the independent variable and the dependent variable are meaningful. Because even though the r squared might be significant, or let's say that the r squared is significant, that doesn't mean that every one of your independent variables had a meaningful contribution to that explanation, that r square explanation that we were able to achieve. And so if the relationship between the independent variable and the dependent variable is statistically significant, again with that t-test, its impact on the dependent variable is stated as higher scores on the independent variable are associated with higher scores on the dependent variable after controlling for all other independent variables. And of course, I have parenthetically lower because it might be an inverse instead of a direct relationship. It might be an inverse relationship, and of course that has to be kept in mind as well. But it's this idea after controlling for the other independent variables in the analysis. And then the B coefficients represent the change, just like we saw with bivariate regression. The B coefficients represent the change in the dependent variable for 1 unit of change in the independent variable, with this caveat that we didn't have with bivariate regression, while controlling for the other independent variables, or while holding the other independent variables constant. So far, so good? And then the beta coefficient is a standardized coefficient, and we'll look at that in more detail today. Similar to Pearson's R. Pearson's R mathematically can't go below -1 or above 1.0, but beta, it doesn't have the same bound, and it's not constrained between -1. If it's not between -1 and +1, you probably have some problems with your analysis. Mostly, I don't say it here, but I say it someplace, I'm sure. It's probably your independent variables are strongly correlated, and that's causing problems with estimation of both the B and the beta. So we'll see that in more detail as we look at some examples. All right. And so here, can't read this very well from where you're sitting, but hopefully you have the notes in front of you. This is just an example with some data that I think it's not theoretically all that interesting, but intuitively I think it'll make some sense for just about all of us. And so it seems like a pretty good it seems like a pretty good example to work through. And what we can do is sort of just work through some of these slides, and at some point I can redo this analysis in SPSS. But I think by this time you probably all can use SPSS and slide over your dependent variable and your 4 or 5 independent variables and click a few other boxes. So I don't know that if we get to it, we get to it. If not, I think you guys would all be able to do the analysis without having that to go back to. So the dependent variable that we want to predict is how often the respondent attends religious service. And so it's just a number that has a minimum of 0 and a maximum of 8. 0 means they never attend a religious service. 8 means they attend, I think it's, I should have some screenshots or some additional details on one of the other slides. I think they're attending, they're somebody that's attending church perhaps multiple times a day or maybe multiple times a week. And so we want to see if we can predict, let's say that we study religious communication, although I don't think there's much in by way of communication related variables here. Maybe we study religion and we just have an interest in religion. And so the question would be is, well, what are the things that we think would be related with how often somebody decides to go to a religious service? And some of the things that I have, and nobody look ahead. Some of the things that I have is, how often do they pray? Does that seem like a reasonable, that should be, as the amount of prayer goes up, what would we expect to happen with religious service attendance? Would it go down? Go up? Probably go up, right? I mean, that's not for everybody, not going to be a perfect relationship. There'll be some noise there. Some people pray a lot and maybe never go to church. Some people go to church a lot and never pray, right? Maybe, but the general trend would be probably that there'd be we call it a direct relationship between those two. As prayer goes up, so would religious service attendance. But it's not causally. I'm not making the causal connection there at all. It's just correlational data. How strong their affiliation is with their religion, and measured on a scale from 0 to 3. 0 meaning strength of affiliation is non-existent. 3 meaning very strong. Whether they believe in life after death, just a dichotomy. Yes, no. How much? So how about this one? What's the relationship going to be here? If we had to predict.
Affiliation is stronger, they attend more.
Right. Belief in life after death? What's that?
I was thinking
No, it's 10 more.
attend more.
Yes.
Attend more. Yeah.
People who believe in life, is it just a dichotomy? Yeah, either, I guess there's no gray area there. Either you believe in life after death or you don't. By this survey. And so those who believe in life after death,
It'll go up.
they probably will go up. And do we think it's going to be? Do we think these are going to be significant relationships, or are these? Would we want to venture, or is this going to be a significant relationship between how much they pray? Which of these are going to be the strongest? Would we?
I think life after death.
Life after death would be the strongest.
I think strength of affiliation.
Yeah.
Strength of affiliation.
Good. And so we could draw some hypotheses up for all of these, right? And we could test those hypotheses, and essentially that's what we're not going to actually write out the hypotheses, but we could if we want to. Then income, what do we think? Income goes up. What happens to?
Religious services goes down.
So, so it's an empirical question that we're going to have an answer to, right? So I don't know what I to be honest, I forget. Nobody looks at. Nobody looks at. I would say the same thing too. I think that I don't know what
I would say Cindy now say curve linear.
It's sort of linear.
curve linear.
Yeah.
In what way?
Like if you're low income, then you go to church, and then if you're high income, you go to church. In the middle is kind of like,
See, I was thinking curve linear too, but I was thinking the opposite way. Like, I think if you're low income and you can't afford to go to church and you can't get there.
No, you go
can't
there
get
for
to
the services.
But in the middle, like if in most of the people that are really rich think they don't need God.
So one is yours is sort of a inverted U, or
Yeah,
yours is
they
a
charge
U,
less
and Williams is an inverted U,
Yeah.
where you're saying the very poor and the very rich
Don't go. as
Don't
much.
go
Don't
to
go.
church.
And I'm saying like,
Highest attendance somewhere in the middle.
Yeah.
yeah.
So like hers is like this.
and
Yes,
his is
but
like
they
Williams
have
is like this.
point,
We
and
could
then
will
it
and when we
goes
get to nonlinear relationships, we'll be able to test this. Why? What's the rationale for the rich? I understand the
The rich, I think that like they have so much money that that's their God, so they don't really need their church much.
and that would be a we're going to be able to test that. Well, not that specifically, but we'll be able to test whether there's a relationship there at all. Age. What do we think?
Older you are, the more you come.
I think so, right?
Yeah.
Education.
I think the more educated you are, the less you
As education increases,
go. Overall, yeah.
yeah. So the good thing is we're going to understand this better than we probably ever thought we wanted to before we're done here. But before we get to that, let's just look at the that yellow box looks a lot better on my computer than it does on that screen. But so if we had no other information. All we had is how often they attended religious service. The mean of religious service would be our best predictor, right? And we talked about this last week. Absent any other information, the best predictor would be to just predict the mean for everybody. And actually, a way to test that, if you don't think I'm right, is you can do a regression analysis where all you include is a dependent variable and no independent variable. So all you have is the intercept. And what do you think the intercept will be equal to? The intercept will be equal to the mean. And you have to trick SPSS to do that for you. But you just have to create a vector that's a constant. Just make it all ones or all nines or all whatever number you want to, but it's just a constant. And then there's a little box that you can say don't include the intercept, and you just include that. One independent variable that's a constant, and then it will probably give you a warning of some type, but it will produce the mean for the as the best predictor. And so you remember this as well, that the amount of error in prediction, if we use just the mean, is the sum of squared errors for religious service attendance. Anybody remember the formula for the sum of squared errors? Anybody remember how to calculate standard deviation? Yeah, and so what's the formula for sum of squared errors then?
The value minus the mean,
Yeah,
and some summation of the value minus mean.
but you have to do one thing to that before you do that. Square it, yeah, because it will sum to 0 if you don't. So it's just this, right? It's the sum of each xi minus xr squared, and we call that sum to squares. Sum to squared errors. And so we also know that variance equals sums of squared errors divided by n minus 1, right? So if we did this, that's equal to variance, right? And then the square root of that is equal to standard deviation, right? Is that right? Yep. And so recall that variance equals the sum of squared errors divided by n minus 1. We can obtain the sum of squared errors by multiplying the variance of religious service attendance, which somebody tell me what that number is. Can you see it? Does somebody have in front of them? Is it 3 or 7? Is it 3? Is it 7 point? The variance.
The bear.
7.35.
7.35, 3. I guess I have it written there too. So the variance is 7.353. I can take that times our list-wise n. What's list-wise n? We've talked about this before.
It's with the cases that you found to be outliers excluded, list-wise.
Missing data.
Or missing data.
Yeah, so it's removed everybody that has, for this analysis, if they were missing any of these variables, they were excluded from the analysis, and we'd say that they're excluded list-wise. Not quite sure why they call it, I don't know what a better name for it is, it's just list-wise. I guess we just go across the list, and if they're missing, I'm not quite sure of the origins of list-wise, but that's what list-wise, in this case, it's the list-wise n, it's not the total n that we're working with, it's just the list-wise n. And I get 8,330.949. And we can look at that number as being a measure of accuracy of using the mean of religious service attendance to predict somebody's religious service attendance. And our hope would be that we want to decrease that. We want to make fewer errors with our set of independent variables. And so that 8,330.949 is just an important number to have some conceptualization of that, because that's our sort of starting point. That is if we only use the intercept, this is what our errors are going to be. And how much can we reduce that if we add independent variables? And the way that ordinary least squares regression works is it's going to reduce that. Those b's are calculated in such a way that there is no other b that you could use that would get you more accurate predictions across all of your data. And so, of course, there'd be, if you weren't looking across all of your data, if you were just looking at each individual person, you could come up with better predictors. But if we look across all your data, there's no other value that we could use for B that would get us, that would allow us to reduce this any more than the calculations that we get with the procedure that we're using, ordinary least squares regression. And so so there's our dependent variable, never to more than once a week. So it's not more than once a day. It's more than once a week. And so we could quibble about whether we would call that interval data, right? It's certainly not ratio. It's certainly not ratio. Potentially, they could have just asked, how many times do you attend? That'd be kind of wonky too. How many times? If you ask them a week, well, I go on Easter and maybe some other holiday, and so what do you want me to give you? Do I divide that by 2 divided by 52, or what do you want? So it'd be I think difficult for people to process. So there might be different ways. There would surely be different ways to get at this. This just happens to be with a general social survey. So professionally collected data done by really smart people that they do this for a profession, and so a lot of thought has gone into this. Doesn't mean that it's perfect, but a lot of thought has gone into it, and probably it's certainly be a good place to start if we were interested. And then you can see some of the other variables and the scales that they're on. And this will be somewhat helpful. This will be somewhat helpful as we go back and try to interpret some of the results. And so this is a correlation matrix, and we can ask, when we do our regression, we can ask SPSS to give us this correlation matrix. And there's a couple things that, well, this is sort of a strange correlation matrix in that the correlations are on the top part of the table, and then the t-test is what it is on the bottom half of the table. And so, for instance, this 0.478 is the correlation between how often they pray and how often they attend religious service. And this number here, rounded to 3 decimal places, is the p-value for that same correlation, right? So above are the correlations, below is just the t-test for the correlations. And a pet peeve, some people see this and they say p is equal to 0. It's not though, right? It rounds to 0 at 3 decimal places. So don't, it's a sign of, what is it a sign of? How can I put this better?
Misunderstanding.
Yeah, thank you. That's it's a sign that somebody misunderstands what we're doing with hypothesis, because p is never equal to 0, right? They say p is, and look in manuscripts, you'll see people do it, and other editors and reviewers don't catch it. P is equal to 0. Well, no, it's not. It might approach 0. It might be 0 at 3 decimal places. You could double click on this in SPSS, and you'll actually see 0.000 and maybe a bunch more zeros, and eventually you'll have some number there. So what would you put? It's not equal to 0. You just say less than. Yeah, that would be probably the more typical way to.
But in a manuscript, in a table, reporting in a table.
What's that?
In a manuscript, if I'm reporting in a table, could I mean, is it traditional just put 0 and then like my asterisk for.
It's not 000 though, right? It's.
Correct, but in the table.
Why would you put 001 or less than 0.001? It doesn't convey. It conveys no information. The 0.000, and it might be 0.0000001, which of course you don't need to put this many zeros in that table, but you could put just less than, or you could put in scientific notation if that was something that you really want to convey, and they would all be the same size. But so getting back to this table, and they're all one-tailed tests too here, which I'm not sure why SPSS defaults to one-tailed test here. When you do correlations anywhere else, it's always a two-tailed test, and two-tailed would probably be the preference. But this is really more for diagnostics. And the top, I wouldn't pay much attention to this at all. Very little attention to the bottom half. I would pay attention to the top half. And of course, on the diagonal, we have all ones. And why are they all ones on the diagonal? Right, and so the correlation between how often you go to church, or religious service, sorry, and how often you go to religious service, the correlation is perfect, 1.0. So on the diagonal, we have all ones, and then above and below the diagonal, you only need to read 1 to 2, right? Because you can fold it and they're the same, right? 0.9 and 0.9, and 0.1 and minus 0.3, 0.1 and minus 0.3, and so you only need to look above and below, above or below the diagonal, because it's the same information. And so if we go back and think about our variables, the strongest one is, somebody said this, right? how their strength of affiliation is the highest correlation, and the lowest is education, right? And so those are just bivariate correlations between our independent variable and the dependent variable. If all of these correlations were really, really small, let's say they were all less than 0.01 or 0.025, something like that, it doesn't bode very well for your regression analysis to be meaningful, in that in all likelihood that the f-test to test the r-square is probably not going to be significant. So that's one thing that's I think can be just helpful, is to look at those relationships. But we wouldn't look at these relationships and then determine our hypothesis, right? That would be what's the word we use? Huh?
Sketchy.
Harking, but sketchy. Yeah, that'd be kind of
Shady.
harking. And what's that acronym stand for? Hypothesis.
After results.
Yeah. So if you run your results and then write up your hypotheses, that is sketchy. That's almost too nice for what that is. It's shady. That's one where you shouldn't sleep for a couple weeks when you go home, and then feel guilty and come back and I don't know what you do at that point, because you've already done it. So you can't undo it, but maybe you'll learn your lesson. The other thing that's probably equally important, or if not equally, maybe even more, certainly less, is to look at the correlation between the independent variables, because this is the thing that we call multicollinarity, where if we have strongly correlated independent variables, either directly correlated or inversely correlated, they cause problems with our estimates. What two variables have the strongest, in absolute terms, correlation? Two independent variables. Is it the 0.491? No, I'm looking at with the dependent variable. What is it, 0.368?
Yeah.
So it's the correlation between how often they pray and their strength of affiliation. Is that the highest one? In absolute terms, it looks like. Next highest would be what?
Life after death.
0.28? And that would be
Life after death.
and prayer, yeah. And then some of them, there's just not much of a relationship there at all. 0.010 between income, is that between income and, is that life after death, and highest year of school completed. Almost no correlation, right? Is that what this is? So certainly not a statistically significant correlation, as we can see by 1, 2, 3, 4. The 0.365 would be the p-value.
Did we determine what too high was?
We didn't. So what did we say last week? Somebody asked what too high was, and I probably punted. What? Huh? What did I say?
I thought you said if you had to throw a number out there, you'd say 0.7.
Yeah, and so we can go with that. And 7 seems high. These wouldn't concern me, and we'll look at some diagnostics next week that will definitively tell us whether they're causing problems or not. But I don't think these would. If I saw these, I wouldn't be particularly concerned with a 0.368. And so I think anything under 0.5 probably is going to be safe. That 0.5 to 0.7 there might be problems depending on what else is going on in the analysis. Then when we get above 0.7-ish, that's when there's probably always going to be some problems.
I'm just looking at these numbers from like from a perspective thinking these are all not too large data sets, good for like a medium sized. Because for a large data set, wouldn't
The p-values would change, but the correlations wouldn't be. The size of your data set shouldn't, I mean, all things being equal, shouldn't change the magnitude of a correlation. But p-values go down as n goes up, and so that would be the thing that would change here. But this is a fairly, what did I say, 1100, n is equal to 1130 or whatever it was, 1113. So it's a fairly, we have enough data to work with here. It's not like we're, if we were to do, what kind of analysis? We could do what kind of analysis to determine our n? Power analysis, yeah, that's just too easy, right? So we could have done a power analysis and determine what our n is, and I'm certain that in our case we probably have plenty of power. William?
Since like one of the questions kicked out like half the participants, would you consider like removing that question? Like, cause I noticed that like
Which one?
there's belief in life after death. Like over 50, I think it's like 53% of people didn't respond.
Which one? Strength of
Bottom right, belief in life after death. So
yeah,
7.4%.
yeah, and so it just would depend on how and maybe you could do a couple different analyses that you'd report. Yeah, because if this is what is it says that there's 1,393 missing, and so yeah, it would be worth it if we just took this one out. Would our n jump up to something closer to 2,700? And here we only have 1,300 too, right? So this would be another one that would cause us because I have a fair amount of missing data. And so this is one of the missing data here is because they try to be economical in what questions they ask everybody, and not everybody gets all questions. So it's not like the people said, no, I'm not going to answer this question. Some of them might have, but in most cases it's just because the person didn't get that question, because if they ask everybody every question, they'd be on the phone with everybody for probably the better part of an hour. So
They didn't give a I don't know one for life after death. I feel like that's a question a lot of people are like, I don't know.
I guess there'd be some. Why not force people? The counter would be, well, why not just force people to? Do any of us really know? I mean, I get maybe we do. Yeah. So I would. I think it's debatable.
DK mean don't know?
Huh?
Doesn't DK or missing mean don't know?
Yeah. So what's the number? 151. So I guess if that would be that was a response.
So they all have that.
Yeah, but that would be not. They probably said, do you believe in life after death? Yes or no. And then if there's a pause, we just need a yes or no answer, please. Do you believe in life after death? Well, what the hell? I don't know. And then they would probably code them as they don't say, they didn't give them yes, no, or don't know. Don't know is only if they won't give you a yes or no, and they might give you a DK. But yeah, I think that would be an interesting, in terms of just developing questions and do we give people the option there, or do we force them? I think in some cases forcing them to choose between two tells you something that you wouldn't get if you gave them that other. But I think there's clear arguments both ways. So I think very good point. So we're here, and this should be the same as what we saw last week. So our assumptions are that our continuous variables are normally distributed or they approximate normality. Again, interval or ratio level measures, with the exception of dummy-coded or dichotomies for independent variables. Our model needs to be linear. We can test we'll do the income test. It just takes us a couple minutes when we get to looking at nonlinear relationships. Independent observations, anybody remember what's that? Our observations need to be independent. How do we define that?
Participants should not be related or should not belong to say a similar group.
When we talk about snowball.
Yeah, so snowball sample would be sort of the classic violation of independence of observation, or independent observations. And it's just that all of the tests that we use assume, you think about a binomial distribution where we're flipping coins, right? If I flip a coin and I get a heads, and then I flip it a second time, does it matter the first time? The observations are utterly independent of each other, right? And that's the way that the statistical tables that we use to test our data they're all built on that assumption that there's not a connectedness across the data. Again, you can take that to an extreme, and it doesn't make any sense. We're all, employed or work at, or maybe we all don't work at the university, but we all live in Norman, or we're all residents of the state of Oklahoma. And so it's sort of once you start, you have to, I think, just be careful that there's no obvious violations of that. And there are some tests that one can do to examine that if it's a concern. And then the multicollinearity and the extreme, where two things are perfectly correlated, or maybe one thing is perfectly correlated with two other things, would be the singularity. And so we'll talk more about that as we move forward. And so when you run your analysis, there's this box called statistics. And I would recommend estimates and model fit are those little boxes are checked by default. I would recommend getting the descriptives and the collinearity diagnostics. And then we'll talk about case-wise diagnostics in the next class period, and so we'll fiddle with this a little bit more. But I would just put those two boxes, and then the correlation matrix that I showed you earlier with the p-values in the bottom half. If you click covariance matrix, it produces a covariance matrix, and then below it produces, for whatever reason, the correlation matrix. And so it's not particularly intuitive as to why it does it that way. But if you want that correlation matrix, you can ask for it. So, but typically at this stage, you probably have already looked at some of those things. And so then, just moving on. So we ran our model. We had our dependent variable, which was how frequently they attend religious service. How many independent variables did we have? 7 independent variables. Is that right? Should be.
6, 7.
1, 2, 3, 4, 5, 6. So degrees of freedom here. What are degrees of freedom regression? Somebody look back. Is it just K? I thought it was K minus 1. Somebody have the notes from last week?
K, just K.
Just K. So we have 6 independent. For some reason, I was thinking K minus 1.
The sum of the squares total is n minus 1. Oh, and the sum of the squares residuals is n minus k minus 1.
Okay, that's where I got the minus 1. So sums of squares regression is just. So if you want to know how many independent variables you have, you could just look here, and it's K. In our case, we have 6. And so remember the f-test, this f-test is testing whether this r squared, which is 0.363, varies significantly from 0 or not. Because just by chance, r squared is not going to be exactly 0, even if we had just a bunch of garbage independent variables, just randomly generated independent variables, r squared isn't going to be exactly 0, so the question is well, is the relationship between the group of independent variables and the dependent variable, is that a meaningful relationship or not? So 0.363, think back to probably week 2, is that small, medium, or large? R squared of 0.363, what's small? R squared? 0.01? Was it 0.01, 0.09, 0.25? We have that 0.01, 0.09, 0.25, I think.
Yeah,
Is that right?
0.01, 0.09.
So we are what? We're 0.3. We're beyond large, right? We're 0.363. So we have explained 36%. One way to look at that is we have explained 36% of the variability in religious service attendance. Now, by variability, it goes up and it goes down from person to person for a whole host of reasons. We've explained 36% of that variability, which is large. And so if happiness was variance explained, we probably would be quite happy with our analysis here. And so the R square, also called coefficient of determination, again, I think Amy Johnson would be the only person that would call it that, is the proportion of, to her credit, is the proportion of the dependent variable variance that is explained by the independent variable. So question, can you calculate R squared by examining the sums of squares?
Yes.
So what would it be?
Sums of squares regression divided by sums of squares.
Yeah, and so it would be, somebody want to put that into their calculator? 3, because this is what you're going to do for the homework number 2, right? You're going to do 3,027.161 divided by 8,331.129 should be 0.363 ish. Similar.
Yes.
Good. So, and then we talked about, and this was sort of my folksy vernacular, the sums of squares regression and sums of squares residual. I called one of those good sums of squares and one of them bad sums of squares. Which one was the good one? Why is regression good? Why would I say that? Why isn't residual good?
Residual references the error in prediction. So I want to minimize the error in my prediction.
Right, and regression is just not, it's not residual, right? It's what you've actually explained. And so, again, if the idea is happiness is variance explained, then sums of squares regression should be good sums of squares, because as it gets higher, we are explaining more variability. And somewhere I say that the sums of squares regression, if we changed any, we'll see all of the b values here in a minute. If we changed any one of those b values up or down, and we calculated total sums of squares regression again, it would only get smaller, and sums of squares residual would increase. And so that's sort of the that's sort of in some ways it's almost, I don't know, you probably don't think about it this way. It's almost a magical in a way that we can take this set of, 1,100 observations and 6 independent variables and have a machine in a snap of your fingers tell you what weights should we apply to each one of those variables in a way that minimizes the error that we make and maximizes and any change that you make across any of those independent. To me, and then maybe that's why I do what I do. It's kind of it just seems it seems like a very powerful, and it is. It seems like a very powerful tool that one can have to understand social phenomena. And so you'll see that the sum of the squares total, that 8,331, is really close to what we calculated earlier. The difference would just be rounding because there's a fair amount of rounding that's taking place, and so the difference would just be some rounding that takes place. And so this is the same. So would we be able to take, and this is a good exam question, in-class exam question. If I gave you that ANOVA table, would you be able to calculate for me the standard deviation? Somebody calculate the standard deviation of the dependent variable from the ANOVA table.
said the standard deviation of the dependent variable.
Mm-hmm. Everybody got it? What would you do?
So it's the total divided by n minus 1 square, and the result is square rooted.
Yeah.
I don't know how to do the square root with Excel.
And then what is n in this case? And what is n minus 1?
So n isn't n 1,133?
Yeah, look at the slide where I gave you the degrees of freedom last week. What's the degrees of freedom? So degrees of freedom for regression is k. Degrees of freedom for residual is n minus k minus 1. Do I give you degrees of freedom total? I don't, do I?
Yeah, the total is, the degrees of freedom for the sum of squares total is n minus 1.
So, and that makes sense. That makes sense because we're adding back in k, and we're taking k minus 1 to get 1127. We're adding, because 6 plus 1127 comes to 1133. So it just would be, so that is n minus 1.
Right, so I do
Right.
1, 1,
Right.
3, 2.
Right. And then take the square root.
And then the square root of.
And then that should equal the standard deviation that I reported on one of the earlier slides. And so, again, what we're really hoping to do here is to take that sums of squares total and in a meaningful way better explain, because the sums of squares total, again, is the squared errors we'd make if we just use the mean to predict everybody's religious service attendance. And we want to reduce that because the mean is just that sort of if that's all we have, that's the best we can do, but it's sort of a brute force, not particularly informed. It's not informed at all, to be honest, way of making that prediction. So we want to see if we can reduce that. And so let's see if we can get through the rest of this slide, and then we'll take a break. So sums of squares regression is the sums of squares of deviation of each predicted y from the mean of y. So it would be calculate the predicted y, determine what the mean of y is, and take the difference between the predicted y and the mean of y, square those, and then sum them up, and that would be equal to sums of squares regression. Sums of squares residual is the sum of the squares of the deviations of each predicted y from y. And so there'd be no sense, and you wouldn't have to calculate both of them, right? If you know one, if you have the total, and you know what the residual is, because the residual I think is a little bit easier to calculate than the regression, although probably not much. If you have residual, you can get the regression. If you have regression, you can get the residual, as long as you have the total. And so then, just as a reminder for the last time, that this procedure that we're using, ordinary least squares regression, determines the b's to associate it with each independent variable so that sums of squared regression is maximized, and therefore the sums of squared residual is minimized. And any other b that you might try to pick would get you only a lower sums of squared regression. And if you sort of think about it, if we had nothing better to do, we could take our data and start picking b values, right, and then calculating, just start with a bunch of b values and then calculate what's the sums of squared regression, and then do it again. It would take us forever, right? If we had to do, and so we're just sort of randomly. We would start off by just sort of randomly picking some b values, calculate what the sums of squared regression would be, and then we could, God, if we had nothing better to do, we could spend 2 months just coming up with different values for b in a way that would maybe after a couple months of doing that 8 hours a day, maybe we'd get close to, just by using sort of a process of elimination, maybe we'd get sort of close to what a machine is able to do for us in, a snap of the fingers, but maybe not either. I haven't fortunately had the chance to sit down for a couple months and do that. So let's take a break, and I'll shut the video off, and in about 15 minutes we'll finish up.
This is your note-taking hammer?
Chris, you plan to do that now? I'm about ready to run out of juice here. Okay, yeah, maybe.
What? Yeah, I saved it, but I forgot where I saved it, so I'll find it.
I was recently reading that you can't report in sentence in APA and make the table.
You can do what?
You can't write out, annotate your significant or non-significant results and make the table. So I guess I was doing both. So I was thinking, I can probably just make the table. And then when you said that sometimes significance is 0.000, I've never really ever got that. But if I get it and I make just the table, so and I would have my notification at the bottom that 1 star is less than 0.05, 2 is less than 0.001, and so on. So in the table under the P column, could I put 0.000 and put double star on the top?
I'd put my preference would be just put less than 0.001.
In the table itself?
In the note. And then so you'd have 1 asterisk is 0.052 is
correct.
0.0.
So I wouldn't put any figures there. I would just put the asterisk.
Right.
Sometimes
That's why
what you do for non-significant, you put NS.
Right, or no asterisks at all, right?
Oh, correct. Okay.
I think, yeah.
Okay. So
But there'd be a number of ways of doing that, but that's probably a common way.
Okay. Thank you.
Oh, there it is.
Did you
you get Jasmine's email about us leaving early today?
Yeah.
I did.
Okay.
I figured you did. I just figured you were busy and didn't reply.
Didn't I reply? Yeah, so yeah, but I remember reading it. So
Okay, fine. Okay.
Yeah, yeah. Right. That was the.
Look at his email. It's interesting.
Yeah.
Go ahead. And then I looked
We
at
got
the email,
it.
no, that doesn't.
I just didn't read it.
And so
I
5
didn't
minutes
read it.
later. No, it was long, but I was wondering about the summer thoughts.
You
No,
should
is it-
ask Christy. Or ask Chris.
Or email the email back.
Ask who?
Chris.
Chris
This
knows
isn't like me
everything.
asking questions.
Yeah, right. From that conversation at the coffee shop, like, I don't know, 3 hours ago? Yeah.
It's a simple question.
What's up?
Did you send out another email, Marissa, that I didn't get?
It says students of the spring .5 GA appointment qualify for applicable summer waivers when enrolled in the summer.
Oh, I wasn't listening.
That's
Sorry.
cool.
Oh, what?
It says students of the spring .5 GA appointment qualify for applicable summer waivers when enrolled in the summer.
But it doesn't say just 3.
It doesn't say how many hours, but
That would be a Christy question.
Yeah, that's a Christy question.
That would be wonderful. 'Cause
Chris,
I know you get like one class covered. Yeah.
I didn't know we got any classes covered.
I think it's for every class you take.
Or was it because I only took 6 hours? See, that's why I don't know, because I only took 6 hours this semester.
yeah,
And I was still
What
in
you're gonna wanna
5.
do is,
I'm a
there
5.
are,
Set up.
This is my
there's
first year.
things all right there.
Okay.
You need to check.
Yes.
I think you need to run it from the flash drive.
So I can check this now.
No, I wouldn't.
You wouldn't?
Well, you can eject it and plug it back in, but I think you have to run it off of that flash drive.
Oh, okay, until I get it
Yeah.
run, okay.
I could be wrong, but. I think you have to double click on the one that's in the flash drive, not the. Oh, maybe not. Plus, there's another file you're gonna need in there.
This one or that one?
The top one.
Like,
I will leave that.
either one, okay.
I know you at French SPSS.
English will be on the install. Okay, so just hit
Yeah.
show us from this.
Oh, this is
No,
really
you're
good.
good. I still need to talk. I assume she's an international student, but I don't want to make any assumptions, you know what I mean?
Yes or no? No.
You don't need it unless you plan on doing this. Well, no, you don't. That's my boss. That's what hers.
there for a second because I thought it was responding to an email. But I mean, you know,
You mean
that it was
reply?
yeah.
Yeah, it is. I don't care. You're the last person to look at that.
Exactly.
Okay, I just got this message.
Yeah, that's why I think you need to run it off the flash drive instead of putting it on the desktop. You're gonna have to cancel it's not gonna let you do it. Actually, you just said that she's already the girl was already contacted him. She was desperate to get that. I didn't cancel. Yeah, it'll work.
For this assignment. So for the dependent variable, she said we're gonna have 5. I think it was 5 you said.
No, I gotta finish this email.
For duties,
For the data for the whole class you're talking about, or for this
for
assignment?
this assignment, number 2, second assignment.
One.
We can have 4 IBs,
That's
and then
right.
how many DBs? 1 D, okay, but in that 1 DB, it's 5 items she said we can have.
Presentations are organization related.
You could have as many items as you needed in that, but it would all be one variable. So if you're adding together maybe the
Okay.
results from 10 questions, that
Yep.
would be fine.
Yep,
But it
okay,
would all be one
okay,
column of data in your data set.
okay, perfect, that answers my question. I'm getting confused between using
Yeah, which is a huge.
variables and using items. Because the items can make up a variable, so you want a variable.
To be honest, I don't care what you do.
Okay,
It's got to be one or the other,
okay,
obviously. And it would really be a matter of sort of your theory and your what you did with your data,
okay,
and it's more about that than it is about an assignment, because
okay.
the dependent variable could be a single item for sure,
Mhm.
or the dependent variable could be some composite of a bunch of items,
Okay,
and it doesn't, for our purposes, that doesn't matter. But theoretically, and with your data, it probably does matter. But
okay,
so
okay,
you just sort of need to let that sort of guide what you do.
okay, okay, that makes sense, thank you.
And I just asked her, did I get it? And so how many hours?
I think it's as long as it applies to your program study.
I don't know. I don't have one yet. I don't have that meeting until the fall.
I think that's good then. I think we're still good. Maybe I should have.
I did that a lot. I knew exactly what it was too.
Either way. It was fun. I couldn't play too much. I was told it was a waste of money. I was really Either way, we'll land wherever I think
Marissa, how many students do you see? How many undergraduate students do you see a day?
A day? On a really busy day, I'll
Yeah,
see
so
like
like a lot of
6.
questions.
But on slower days, it's like 3 or 4. Right now, it's not so bad.
And you and Shay split them up based on alpha or what?
They actually can sign up for whoever they want. So if they've seen me a couple times, typically they'll keep coming to the person that they know. And then Shay has people that she's been advising for years, like
Right,
since Jay
right,
freshman.
right.
So I kind of like have my students and she has her students that we've seen. And
You
then-
get to know them?
Yeah, it's nice.
What's that?
They're nice kids.
Of course they're, right? Yeah.
Yeah. I mean, sometimes Natalie has advice too. Sometimes you're like, bless your heart. Like you have hot mess students, and it's always a hot mess every semester, but you still like them.
Yeah. Mm. We spend a lot of time. You know Kathleen Shay Smith. You maybe don't know. Shay would know her. She's the associate provost for over advising, and her and I work together on a lot of different things, and advising is one of them, and it's just so important to the success of students
Amazing for students that are misadvised in university college, so they come to us with classes that they didn't need.
and University College would say they're surprised at the students that get misadvised in the departments, right?
I know.
We've actually done a lot of focus groups with students on advising, and it's quite variable. There's some places that they maybe like you and Shay, they have a relationship and they get what they need. Plus, they might get some other support that they need about or advice or whatever, just somebody to talk to about a hard semester or whatever. In other cases, it's just very much the process. What do you need to do next to move along on the process? And it's all about process, none about relationships, right?
Shay shared with me some of the results that they got from that survey about students' experience. I think it was a very general survey, and it said that one of the things they were the least happy with was advising. And I just thought, oh my gosh, I know Shay and I put a lot of effort into advising and developing interpersonal relationships with students, following up.
I wonder what would your students say?
I think my students would say they like being advised.
Did they get what they need and
Yes, and that we're
I think it's
responsive
different
and
when you're
open
like
and
first-time freshman versus major student. Like, it's
what
definitely different.
first time freshman versus what?
Yeah, like having freshman sophomore advising is a lot more intensive because you're teaching them how to be college students for the first time versus major advising where they've kind of been socialized and
But you still get the hot message.
yeah, no.
how to register on Facebook. I literally have seniors who don't know how to register. So I bring them into my office.
Because it changed or something changed or they just
I don't know why they never asked me. Yes, register the classes. I kid you not, and multiple teachers, not just one.
maybe they just know that you're friendly and you'll do it for them and if I could get you
No, I'm like, sit down, get your laptop out, learn how to use this. It's amazing. No, that part is a little bit frustrating, but I think they know that Shay and I were really committed about them. We remember, like, talking about classes.
So if you ask Shay about Kathleen, she knows Kathleen because she's working. Yeah. So Kathleen told me the other day because my only experience with actual advisors is in the comm department. My office used to be down there, so I never knew Shay, and I don't think I'd know her if I saw her. But Kathleen, and for some reason I was talking about, in the comm department, and I don't remember what I was saying. This is what they used to do. And then she mentioned Shay, and she said that she thinks Shay is one of the best advisors on campus. You tell Shay that. That Kathleen said that.
And we not use the word, I don't know if she knows it, but we want way too much advisors.
Oh, good. Well, if it goes through Kathleen's office, she'll get it for sure, but it probably doesn't because it goes to the college.
I got a couple of students who
Yeah, yeah. Like, and I'm just gonna be very
she
careful.
deserved it last year too, but hopefully she gets it this year. She's good enough. But I really
Right,
really
you just think of
like
it.
she trained me really, really well.
I'm trying to be very careful not to. I'm 90% sure, but like at the same time, I don't want to be like, I'm assuming you're I don't want to make any assumptions.
She is always way to do what she does.
Give me the
And
I also.
Good for you guys, yeah, good for you guys.
And I feel like she's
Literally
really
coming there and just
the
from
really
there's.
important values and
Is that
and
good?
advising too.
I really just
Yeah, yeah. That's why I'm curious what would the students say, because if you talk to advisors, a lot of them say the same things. but then you talk to students and sometimes there's a disconnect.
Yeah.
And of course, there's going to be some grumpy students that they'll never be happy, right?
Yes. And I have students that are like,
Tell her that Wayne thought she was the best advisor.
she'll love that.
Okay, let's get started. I would have totally forgot.